Okay. بسم الله الرحمن الرحيم والصلاة والسلام على أشرف المرسلين سيدنا محمد وعلى آله وصحبه أجمعين. Assalamu alaikum everyone. So as usual, we're going to be starting with a recap of what we discovered so far, what we discussed so far, inshallah. So last lecture, I give you a glimpse about what you should expect the course to be about. We said we're going to be looking at geometric modeling and control of robotic systems, and in particular, we're going to be focusing on two classes of robots, which are multi-rotor air vehicles and fixed base manipulators. And we said that even though these already the tools that we're going to be discussing will give you already a lot of ground to cover, there's even a wider class of robotic systems that we will not be able to cover, which are known as floating base manipulators, or in general vehicle manipulator systems, which are simply robot arms that are on moving other moving robots. And we said that the kind of tools we're going to be learning here are actually extendable to this kind of system. So the same principles they hold in both cases, whether you're working either in these two classes or in this general class of robots. Said that why would you go for the geometric approach, which is this is only one slide that convinces you, that should convince you that why the course is important. It simply is that the configuration space of most of the mechanical systems is not Rn. And whenever I say Rn, I mean linear algebra. The first thing that should come into your mind is linear algebra and all of the tools that come with that. So matrices, taking the determinant, taking matrix multiplication, taking the inverse of the matrix, and all of this, all of the tool set that comes when you're working with Rn. And then we said that the configuration space of the interesting mechanical systems that in the end make up what we call robots, okay, the physical robots that we're talking about, they're actually not Rn, and usually they have some sort of non-Euclidean structure. And then when you try to apply, the linear algebra tools that you're already familiar with, when you go to these kind of systems for modeling, for control, for doing advanced stuff like doing learning or model-based optimization and stuff like that, you face a lot of trouble because of just the limitation of the tool set that you have. So this is the motivation behind the course. And we said that in the first topic, what we're doing right now, so this is the first 5 lectures of the course, inshallah, we're going to be looking at this idea of structure, which is, we'll be looking at the mathematical foundations that we need in order to continue and move on later on to the actual robotics. And last time we discussed about sets, and I'll do a recap very quickly of what we discussed last time. And then we said the term space, which you hear a lot. For example, you hear something called a vector space, you hear a group, you hear a manifold. All of these terminologies, they are all referring to a space, different types of spaces, and in the end, each space is just a set with extra structure. Today will be the first time we're going to be talking about an example of this extra structure. So we're going to be building it bit by bit. So the most abstract concept is a set. And after that, once you add more structure to it, once you have more stuff to do with operations or extra set that defines some sort of certain properties, in the end, you can work with this higher or more advanced object. Okay. Yes, please.
This table, it is called the axiom method or what?
No. This is, it's not called anything. This is just, what you see on top are usually higher level structures. This is what the table indicates. They are higher level in this structure that usually include the ones that are on the top. So when you see here the set to being the bottom, which means that there's nothing beneath it. It's like the most fundamental object that usually everything else is based upon. Okay.
Explain as well.
No, it's just I'm maybe in the mathematics, but I'm not aware of this stuff. Okay. I think it has something to do with category theory. Maybe if you want to look at this different categories or stuff like this. I'm not sure. Okay. What is a set? Just to recap, a set is intuitively a collection of elements inside. So they could be same elements, they could be different elements. Doesn't make a difference. Okay. And in the end, we have certain notation. Whenever we say X belongs to, so this notation we read it as X belongs to S. You can define a set by all of the elements you have inside by just stating them one by one. So it has a square and a rectangle and a triangle and a blue square and a red triangle and so on and so forth. Or you can define them by restricting a bigger set. So for example, in this notation, it's read as A is defined as the set of all elements X in S such that you satisfy some conditions on X, and in the end, this is a subset of S. And we said we can define new sets from all sets that you already have by simply taking the Cartesian product, which in the end leads, if you have R and R and R, and you take the Cartesian product of them, you have Rn, the usual Rn you're familiar with, and then you have the union of two sets, you get a new set or intersection, and so on and so forth. Now we're going to be looking at something very important, which is the maps between sets. And this is a normal drill we're going to be doing all the time. Whenever we introduce a new structure, we're always introduced with it a different type of set, okay? So the maps will simply be, again, as sets are the most fundamental, object, then maps will be the most fundamental relation, or like, it's already, the name is already well defined. It's like a function or a map between two sets. When we go later on to different types of groups, different types of structures or different types of spaces, we're going to be having also maps, but with more structure that actually will have different names. Okay, so we'll keep on doing this again and again. Just keep this in your mind, and you'll see it's repeating. Okay, and it's a recurrent theme in mathematics in general. So let A and B denote two sets. A map F from A to B will assign to each element of X in A an element F of X in B. So the standard notation for a map is usually written like this. You write F, which is the name of this map that you're talking about. So the name of the map or the name of the function is, and you write where it maps elements from to the set that it maps from to the set it maps to. And then usually you can also write in one line how this map is defined. You can, for example, if I take any element X in A, it maps, and you see there's a slightly different notation here. So this is between sets, and this is between elements in the sets. So an element X in A is mapped to an element F of X in B. Okay, is this notation clear? Yes. Sorry? F is called, in this notation, is called a map. Another name for it is a function. Another name for it is a mapping. Okay? Yes.
So asking that if the element of B necessarily has to be a function of an element of set A, which we are calling X. So necessarily that element of B has to be a function of.
This is something we're gonna be classifying functions based on that. But this is the general definition. So there's actually, as you see here, there's actually no definition. Okay, we did not provide any definition. I just told you if you have something like this that assigns for every X an element F of X, then we call this a map. Okay.
They need to be related or dependent upon each other, or they can be separate.
What is separate from what?
The X and the F of X.
Yeah,
so
but they are related by the F.
It has necessarily be related with the with the element of A. So the element of B necessarily has to be related or dependent on the element of A.
Through F. That's already the definition. You assign to every, yeah. If they are not related, then you don't have a map, right? So another different notations that we're going to be calling A, the domain of F, and we're going to be calling B, the target or the codomain of F. These are just standard notations. And we sometimes, when we have a map that goes, you remember we said that, I think that's related to your question, that we map all elements in A to B, but sometimes we don't map all elements of B, okay? Sometimes we don't reach, in other words, we don't reach all elements in B. And so if you restrict the set B into only the region where in only the set the subset that you map A to, we call this, it usually has the name as the image of A under F. Okay, so the image of A, so this is just the notation. Okay, what is this a notation for? What is all of this a notation for? So what type of object is this? It's a set, exactly. So this set, so you see M sub F brackets A is just the name of one set. You could have called it G, could have called it phi, whatever, okay? So all of this is just the name of a set. It's defined as all of the F of X in B they are all of the elements. Remember, f of x is just the name of the element. All of the elements, you could have called them y, okay? All of the elements in B such that x belongs to A, okay? Another way of writing this, you can say image f of A is defined as all of the elements y in B such that there exists an x that y is equal to f of x. That's another way of writing. Yeah?
By setting that X elements. So isn't this?
It's a set, yeah. It's a set. So you, and this is I think the answer is in the notation. So you see here, this is a set. I cannot define it unless you tell me which function you're talking about and which A you're talking about.
Saying that the condition is that X belongs to A.
Yeah.
Why don't we say, I think we just want to say that, why don't we say f of x belongs to A?
Okay, I see your point. Yeah, okay, I see your point. Yeah. It's a good question. What is MFA? What is the image of A under F? A subset of. Is it a subset of A or a subset of B? Is it a subset of A or a subset of B? It's a subset of B. Okay? So it is the part here that you reach with the map. Okay? And I'll give you an example to clarify things a little bit. Okay? So this is just notation at the moment. Okay? Abstract notation, things will become clearer with some examples. So inshallah, we're going to have a lot of examples that will clarify these abstract concepts. Okay, give it for granted what I said, that, okay, this is the map and these are all of the definitions. Take now classification of maps. So a map could be either surjective, either injective, or both. And if it's both, we call it bijective. So these are, again, names. When do you call a map surjective? You call a map surjective if for every y in B, so B was where you go to, if for every y in B, there exists at least one x such that f of x is equal to y. That's the definition. Injective means if the equality f of x1 and f of x, if you have the equality f of x1 is equal to f of x2, okay, then for x1 and x2 that live in A, this implies that x1 is equal to x2. And bijective is both. Very abstract stuff, very hard to digest, okay, in 5 minutes. And this is why, okay, we have, okay, examples. But before the examples, there is another name actually for surjectivity or injectivity. Sometimes actually this name is already, sometimes helps the definition. Sometimes we call surjective onto, and we call so a map is surjective. Sometimes you call it an onto map. And sometimes the injective is called one-to-one. Let's start with the injective one. When you say you have a one-to-one map, what does that tell you? For each element in X, you have only one element in Y. Take a look at this definition. If I go to B and I find myself, I reach the same element, what does this mean? It means I came from the same element in A. This is exactly what this line says. Okay. And of course, I know it's too much thing. That's why we have nice figures for that. Okay. This is again a little bit of illustration of the concept. Take a look at the figures a little bit. Okay. Try to see whether the definitions match or not. Yes.
Going back to Fahd's question, the image of
Leave that. Wait a bit. Take a look first at the definitions. The easiest one to look at is surjectivity and injectivity. Take a look at D first. A map is surjective and injective if every map in A is uniquely mapped to one element in B, right?
It is same elements? The same elements in both sets?
What do you mean same elements? No, there can be different elements. A and B can be something completely different. A can be a set of squares, B can be a set of circles. Today, this will be a little bit more clear, okay, with a lot of examples.
See, it's not objective. I want element should
C is not injective or not surjective, you mean?
these two
Yes, right. Every element in A goes back. You see, like every one element here has one element there. That's right.
see
A unique element in B? No. That's not the definition. Yeah, I know. But we're talking about injectivity now, right? So this one is not injective. Why is that?
One needs multiple unique.
There are, for one point here, I have multiple sources. So this is not injective. But you see, this one is actually injective because for every one here, I have a unique one there. But why is this one not surjective? There is one left out. There is one element that I can never reach starting from here. There is one element here, at least one element that belongs in this set that I can never reach starting from there. And you see here, for example, this is neither surjective nor injective because there are some elements I cannot reach. And also, sometimes if I start from this one and that one, I go to the same element. Okay. So this is the abstract definition. This is the illustration of that definition. And we're going to have more examples less of the image. Yeah. Yeah. Okay. So, yes. Could you want to answer that? There is a trick that we can play here. What does surjectivity mean?
B can reach all the elements of B.
Yeah. So go back to this equation. So this definition. If I have a map F that maps me from A to B, I can be either surjective or non-surjective. If I remove B and I put this subset, which is this new set, instead of it here, what do I get? Always or not? You're always surjective by definition, by construction. If B is actually the image of A, this is actually another way of calling what is surjectivity. If B is equal to the image, if the set B, where you go with F, is equivalent to the image of A under F, is actually another way of saying the map is surjective. So surjectivity can always be, handled. If I have a map, if I go to a space that's not, if I have a target space that's not surjective, I can always restrict it and I find surjectivity. Okay, so that's easy way. In injectivity, injectivity you cannot solve it, okay, because it depends on the uniqueness of the variable. Yes, they have nothing to do with each other. Completely different sets. Okay, and we're gonna have some examples. These are examples of maps that are both surjective and injective, so they are part of the D class, both surjective and injective. One is actually the identity map. For every set, there is always a map called the identity. I take one element, and it gives you the same element. It's trivial. Okay. If I have real numbers, taking one element here, x, and mapping it to x cubed, okay, which is x multiplied by x multiplied by x, is injective. Why is that? Why is it injective here?
All hit and multiply together.
No.
Because the only way that x cube, x1 cube equal x2 cube is if x1 equal to x2.
Exactly. So you see the definition already. You can check by the definition. Okay. You can also try to contradict it. Does there exist any element here, that will come from two elements here? No, you cannot. That's something else. We haven't talked about it. That's not defined yet.
first X is not, it doesn't, it's completely different than the second X.
Exactly. That's another way of checking the proof. If this one is different, if I have x1 here and x2, and I calculate x1 cubed and x2 cubed, there is no way that x1 cubed will be equal to x2 cubed unless x1 and x2 are the same. It's actually the definition. What you're saying is exactly the definition of the what injectivity is. Surjectivity, is there any element in R I cannot reach by taking the cube? Are there some regions maybe? Of course, now I know what is going on in your head, right? You're all doing what? You're all drawing actually the x cube, okay? And that's why I'm not showing you any graphs here, because of course, when you have R, when you have R squared, when you have R cubed, you can always, can visualize stuff and you can draw stuff. But in general, not. Okay? If you have 6 dimensions, why you might say, why do I need to worry about 6 dimensions? Guess what? What is the configuration space of velocities of a rigid body in general? Will be actually 6 dimensions. So you'll not be able to visualize anything. So this is why I'm training you on this abstract or this analytical way of showing this proof. Okay, so more on that later. Another example of maps that are not surjective and not injective. X square, the map from R to R that takes a map and maps you to X multiplied by X, so X square, is not surjective. Why is that? You cannot reach any of the minuses. You see, we have the set R here, right? Which means R has positive numbers and negative real numbers. If I have any negative real number here, I can never reach it. There is no X that will actually give me this negative real number.
We change R to complex numbers, then it becomes.
You're talking about a different set. Different set and different what? And different map, exactly. So the map, you see, we're talking about different stuff, okay? Maybe the map is the same, but I have different sets, so something completely different, okay? So that's why we're talking about a map F defined like this, and we're talking about the domain like that and the codomain like that, or the target space, okay? Everything is well defined. If you change stuff, okay, of course, the properties change. The same for the sign. So why is this one not injective? Because I can have -1 and 1 here and I get the same number. I can have -2 and 2 here and I get the same number. I can have -1.5 and 1.5, I get the same number, and so on and so forth. What about this map? I cannot reach higher than 1 and negative than 1. Okay, so all of the greater than 1 and less than 1 I cannot reach in R. And what about the injectivity? Why is it not injective? If I check, for example, if I start with, let's say 1, let's say the number 1, is there one unique X that gives me 1? No, there's what? There is pi, 3 pi, blah, blah, blah. Okay, you know what I mean. Okay, so this is an example for something that's surjective and not injective. This is an example for something that's not surjective and injective. Follow the same line of reasoning and you'll find everything, matches perfectly to what just discussed. Okay, so I'll leave these examples for you at home, okay, to go at your own pace. So you see that the abstract definition that we mentioned there, actually, they make sense. Okay, so at least they make sense on their own. You just need a little bit time, to convince yourself and to digest. New definition. Okay, so what we discussed so far are maps between sets, and the classification of these maps as either surjective or injective, or both, which is just what you call a map bijective. Okay? If I have 2 maps, F that takes me from A to B, and another map, G, that takes me from B to C, you can always construct a new map, a third map, that we call the composition of F and G. We denote the map. You know what denote means? Express. It's just like express. I'm gonna write it as. So whenever I write G circ F, what does that mean? What is that object? Is it a set? It's the map itself. It's the name of the map. So G after F, you see, it's the name of the map. Okay? By the way, I could have called it gamma, or map H, or map Ahmed. It's just a name. So this is just a name, and it maps from A to C. If I have a map, it maps from set A to set C. If I have an element X in A, I first map from I go from X to f of X. So I go from A to B. And then what do I get? I get an element in B. And then after that, I can eat that element with the G, and I get an element in C. Make sense? Make sense for everyone? Again, this is, I know it's a lot to take. Okay, so please stop me at any time with questions. Don't be shy. Okay. So G after F, or the map G circ F. The map G circ F is a map that eats an element in A and gives you an element in C. What is this element? Okay, this element is equivalent to, okay, so all of this, you see it's an element in C. It's equivalent to first eating X by F and then eating the result by G. Okay. So for example, the map X power 4, okay, I can write it as the composition of X squared after X squared. Because I first have 1 squared, and then I get the result, and I square it again. This is the definition of X power 4, right? And so on and so forth. Okay. Sometimes you find these diagrams a lot, okay, in some papers or in some textbooks, and they are called commutative diagrams. And they simply just have all what we just discussed on the top. You see here, we have that A goes to, so F maps A to B, and G maps B to C, and then the G circ F maps from A to C. Okay, and follow here you have to be a little bit careful with the definition. This is G circ F, not F circ G, because F circ G is something else. First of all, is F circ G, can you define it in this way? I mean like this, for a general A, for a general B, for a general C. G, so this is G circ F. Can you define F circ G?
F function of G of X.
F, yeah, exactly. It's just F as a function of G of X. Is it defined? Exactly. Exactly. That's the condition, but in general, it's not defined. What you just said is not defined. This is well defined because I know that f of x goes where? To B, and g of x goes to, so I have a map from A to C. But what you just said that f eats g of x, first of all, can g eat an element x in A? It's not defined. Okay. By the way, they can be widely different objects. Where? How?
A, B, and C are defined.
Okay. Can you go back? Okay. Let's have an example.
It can only happen if they are bijective, right?
Right. Okay. So let's see. Can you go back from here to here? From R to R? So if the map is defined like this, can you go back from R to R? For example, if I have here -1, can you give me back an X that's in R that corresponds to the -1?
X is always squared.
So you see, you're talking about the one direction. It doesn't go backward. So it's not always possible to actually talk about this backward, unless you have one condition. What is it? Bijectivity, exactly. So here, let F be a bijective map. If F from A to B is a bijective map, then we can define a new map. We call it the inverse of F, and we are going to be denoting it by this symbol. This is universal. This is defined, and it goes back from B to A, and it has a definition. Okay, it's defined as when you have F inverse circ F. So this is a map. This is a map. You find that you get the identity. And if you have F circ F inverse, you have the identity. But why aren't these the same identity? Because A and B are not the same sets, okay? So that's why this is a map that takes every element in A and gives you the same element. And this is a map that takes every element in B and gives you the same element. They're not the same, okay? And there will be a lot of examples that will clarify this, how can we have, these different sets, okay? Today will be clear, inshallah. Yes.
Would be under the axiom, for example, definition.
What do you mean by axiom definition?
New operation, new something, axiom. Axiom.
Yes, but they take them as like a subset of
like addition, for example, the axiom addition, for example, simple addition.
I don't know what you're talking about. I don't know what you're talking about. So that's my typical reply, because what we're trying to do here, we're not, and this is it's also for when you're studying, okay? Do it, but with caution. It's very nice to divert a little bit and go into the math a bit by bit, but that's a rabbit hole. It's actually a black hole, not a rabbit hole, okay? You can go there and never come out for the rest of your life, okay? Okay, stuff there are very interesting, very widely generalizable, but what we're trying to do here is that we're still engineers, we're still robotics, okay? So that's why we're only covering, the surface only of what we need. So I'm only spoon feeding you only the little bits that what you're trying to do. And we're going to build them bit by bit. Within 5 lectures, you're going to see how much we're going to be covering, inshallah, in 5 lectures. You're going to see how heavy it is, okay? And then if you want to go on your own, okay, there is no limit for that. So I'm not going to answer these questions, okay? All of the wild what if, I'm not going to answering them, okay? So I'll ask them, and then you get my reply. So don't be shy to ask, but okay. If I reply, okay, you know that, okay, you've hit the limit, okay? Or honestly, I don't know, okay? So you can have also 2 sets. So this is another definition. We're going to be calling 2 sets A and B. We're going to be calling them isomorphic to each other. And here there is between brackets set theoretic isomorphic. You're not going to understand what I mean by that unless later, inshallah. But for now, just whenever you see something in bracket, you can just skip it normally. You'll not lose anything. So this is called isomorphic. If there exists a bijective map F from A to B, and in this case, usually you're going to be seeing this symbol, okay? That we say A is isomorphic as a set. This is what the subscript is. The subscript, okay, is not standard actually. So, sometimes you find it in textbook because only for education. If you go to papers, you're going to only find this symbol, and then you should know what you're talking about. And this will be clearer later on. Who saw this symbol before or this equation, A, or like this equality? This is called congruent. Okay, the symbol, okay, is called congruent to B. Who saw this symbol before in some paper or in some book? No, that's different. We sometimes it properly used as an equivalence relation. That's something else. Very good. Can anyone answer that question without knowing anything outside of what's on the board? What does it mean that you have 2 sets that are isomorphic? There exists a bijective map that maps one to the other. That's it. Did I say many maps? What does the definition imply? One map. What if there are many? Okay, good. Doesn't change anything. Okay? If there exists just one map that goes from A to B back and forth, and this is the key thing. If there exists one map that goes back and forth between an A, so A and B are isomorphic as sets. What does that mean? It means that A and B are the same. I'll give you an example. I'll give you a set called 1, 2, 3, 4, 5, 6, up to, I don't know how many are you, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16. Okay. So from 1 to 16, this is a set. What does it have inside? If you take anything from the set, what do you get? A natural number from 1 to 16. Can you get 17? No, it doesn't belong to that set. That's set number 1. I'll give you another set that has Ahmed, Ibrahim, Tariq, Fahd, and so on and so forth. Ziad, and so on. Okay. So these are the names that include all of your names. And then I have a map that says 1 goes to Ahmed, 2 goes to Tariq, 3 goes to Sajjad, 4 goes to Farouk, and so on and so forth. First of all, are these the same set? Different sets. Is this map bijective?
One set defines the numbers.
Yeah.
What's the names
So so the question is, are they the same set? No, because they are collections of different objects. One contains numbers, the other contains names. That's the first thing. Is there a bijection between them? What I just defined right now? Is it a bijection? Does it go back and forth? Yes. Are these two sets this isomorphic? Yeah. If I give you this, if I tell you number 2, stand up, you will stand up. If I say Ziad, sit down, you will sit down. So information-wise, there's nothing else. So this is exactly what we mean by the difference between isomorphic and the same. Okay. So writing it like this, they are not the same, but they are isomorphic if there exists some bijective map that goes from A to B. Yes, Fahd.
A bijective map, which implies that there are could be multiple maps.
That's right. I'll give you another map right now. One in the first map, I'll call it F1. I have number 1 is Fahd, and number 16 is Ibrahim. And in the second map, I have number 1 to be Ziad, and the 16th number, okay, corresponds to Sajjad. Is this the same map? Do they map the same sets? So F1 goes from A to B. F2 goes from A to B. Are they the same map? Is each one of them a bijection? Yes. Okay. I'll give you a map that's not a bijection. Number 1 corresponds to Muhammad and Fahd and Ziad. And number 2 corresponds to, okay, Muhammad and Ibrahim and Bush. Okay.
I think, first set A, for each element, it should be unique. So number 1 should only go to one person, but
Okay.
The number 2 can also go to the same person.
What does that make the map? No. What does that make the map? If number 1 goes to this, if number 1 and number 2, they both go to the same person, what does that make the map? It's not? Okay, so is it surjective? It's not injective. So this is like an example of a map that's not injective, and so on and so forth. No numbers, you see, we're not talking about numbers. We had partially numbers, but it's not a map from numbers to numbers. We're still talking about collections, and we can still define the map, and everything, makes sense. Yes.
So they are not bijective, right?
Exactly.
They cannot be isomorphic.
Exactly. Sorry, no, that's not that's a very good point. If the map if I have a candidate map like the one I propose right now, and you checked it and it's not bijective, does this mean that the two sets you're checking are not isomorphic? Why?
One direction property.
No.
Could be another map that's
Could be another map. I'm trying one map. Okay. There could exist another map that I did not try. So, okay, in principle, you have to try all maps. That's why you see the definition is that there exists a map. Okay. If you can find at least one map, you're good to go. Okay. Yes.
You know, it's not either finance its own, not either injective subject. It can't be bijective. But this only applies for finance.
I'm not sure. I really don't know this. I don't know about it. Okay.
Yeah.
For infinite sets, for infinite sets, things get, this is the weird stuff. Okay. And there are tons of YouTube videos that really, okay. I think I think you can check it out. There's a Veritasium, I think there's a channel called Veritasium, and you can find there, they actually have a nice, I'm not sure if it's actually them, but there's a nice YouTube video that what happens if you have a house, a hotel that has infinite rooms, can it actually go out of rooms or something like that? Okay, so look it up. Okay, this is the weird stuff that, okay, that we're not covering, okay? But this is the beginning of the rabbit hole, okay? So, and this is an example that you see a lot in robotics, and you see a lot, okay, in programming, in machine learning particular. This is a map. We're going to be calling it the vectorization map. This is the name of the map, and it will be denoted by VEC. It's a map from a set called Rn by n and another set called Rn squared. We talked about the Rn squared. Okay, it's the map that it's R times R, it's the Cartesian product. But the set Rn times n, we never talked about it. But you know what it is, right? It's the map, it's a set that has objects of this form. Like they are like 2D, they have rows and columns. And you have a weird name for it, you call it matrices. Okay? So you call this set the set of matrices, the set of n times an n-dimensional square matrices. If I tell you like this, you know, yeah, I know what you're talking about. But for you, what are these called? Okay. This is forbidden word to use here. No such thing as vector yet. Next lecture, you'll know why. These are not called vectors. These are called what, you know, remember what we called them last time? Tuples, exactly. They're just an n squared tuple. They're just one number after the other. R times R times R times R. This idea of, you know, if I have a Cartesian product of R. So I just take one number and I put the other and the other and the other until I make in this order. Are they the same set? No, different object. This is Rn squared. What you think of, you know, between quotations as a vector, we're not going to be using that word. It's just a tuple. And this is what you think of as a matrix. How is this vectorization map defined? If you give me this rows and columns, okay, written an element written like this in terms of numbers organized in rows and columns, I can put them into this vector format, okay? Or I will rearrange them into this form. Can you go back and forth? Is this bijective? Yes. Yeah, the order matters. It is bijective, okay? Then I can always go back and forth from this. You can check it on your own. And actually, it's already, you can do it in MATLAB very easily like this. So actually, this is the command to go from A to V. So A here is an n by n matrix. Okay, and this is the map how you would define, okay, how you would write it as a V. And A back is simply the reconstructed A from given V. Okay, if you have V like this, which is n squared dimensional, okay, or properly speaking, they are n squared numbers. Okay, this is an n tuple, n squared tuple. I can reshape it with this command into an n by n matrix, like with this command. So this is just a side of what you can do it in MATLAB. Okay, so it's a bijective map, and two different sets. They are different stuff. Okay, different objects. Now let's go to the second structure. So now we're done with the lowest structure, which is this one of a set, and now we've considered them without any additions. Yes.
Always has to be inverse. Inverse always exists.
That's right. That's the definition of the inverse. Yeah, that's right. So the set here, we did not talk about any structure, and now we're going to be seeing what do we mean by structure. I've mentioned the word a lot. Okay, now we're going to be seeing what is it exactly, the structure. And we're going to go one level higher. So now we're going to be introducing a new kind of object, a new kind of space, which will be a set plus extra structure, plus some extra stuff that we can do with it. And we're going to be building it step by step. So we're going to be looking at, in the coming, today in the lecture and in the coming lecture, inshallah, we're going to be looking at groups, fields, and vector spaces. Okay, so each one of them is actually a different structure, okay, different kind of space. The map is something that, so you have the set and you have maps between sets. They are all in the same level. They are both the most, you know, fundamental ideas. What is it? What is an F? This you have to go a little bit deep into the mathematics. This is actually related to the axiomatic set theory, and you need to look at what's known as a relation and propositional logic, and you need to go into this direction to know exactly what is an F. Okay. Yes. The maps, you can define the set of maps. That's correct. You can define a set of maps, but a map itself is not a set.
You can define the map as, since it's from A to B, for example.
Yeah.
Take a Cartesian product from A to B. Okay. You can think of the map as a subset of the Cartesian product from A to B.
It's actually, this is the definition of how we do it with the relation. That's exactly how we do it. Yeah. So this is exactly what the relation is. Yes. But you need to go further. You need to define what's known as a power set and so on and so forth. Okay. So now we go to the board. For those of you who are still, this is the first time today. So usually we're gonna have this, you know, most likely every lecture we're gonna have always slides part and the written part. Okay. The written part, this is on your own. Right? Either write everything I'm saying, okay, or either, you know, you find a friend and you come very close and you sit and watch and he writes. Okay, it's up to you. Okay, so we're going to be defining now a new space which we'll be calling a new type of object, we're going to be calling them groups. So this is the definition of what a group is. So definition, a group is a pair G circ, okay, where G is a set. You know what a set is? You know what a set is? Okay. So where G is a set and the circ is a binary operation. In other words, it's just a map. Okay? It's just a map that will eat something from this set. What is this set called? So G is a set. What is this set called? The Cartesian product of G with itself. The Cartesian product of G with itself. Okay. So, and it goes to G. So this is the mapping. Okay, so this is the binary operator. And such that we need to satisfy some conditions. The first one is that if I take one element A and one element B in G, okay? So if I take one element A and one element B, and I have the map act on both of them, okay? This is another way actually of writing the map. So this is, if I have an element A and B, I can map them to, we're gonna be calling elements that are in G that, okay, that this map takes these two elements and goes to, we're gonna be calling it A circ B. So pay close attention to the details, okay? So circ is the name of the map, okay? You all agree? G times G is the set, is the codomain of the map. And G is the target, okay, where you go. So G times G is where you start, G is where you go. So if I have one element A and one element B in this set, okay, I go to a new set. It's called A after B. That's it. Do you know what this map is? No, I mean, do you know what the set is? Which set we're talking about? No, it can be any set. Do you know what this map does? It can be any map. That's it. Stay at this level of abstraction, okay? It's a map that goes from the Cartesian product of G with itself to G. Can you do that here? This is a set and this is a set. That's okay. Are they the same set? Are they the same as, okay, an exam question. Is the codomain and domain of this map the same? Who says yes? You're laughing, so is that a yes? Yeah. You have no idea. Okay, what do you mean by the domain? Where the map goes from. What do you mean by the target or the codomain? Where the map goes to. Where does this map go to? To G. Where does it come from? G cross G. Is this map the same as this map? Sorry, is this set the same as this set? No. Very easy. Is 1 equal to 2? Is 1 the same as 2? It's logical. I know it's a little bit, yeah. Do you need to, is it really that simple? Yes, it's really that simple. So it's, I know this is the difficult, oh my God, this should have been an advanced course in mathematics, right? But these are very simple stuff. It's very abstract stuff, okay? The difficulty is not what's written on the board. The difficulty is that you're trying so hard to try to relate it to robotics and building robots and, you know, and flying drones and all of that stuff. This is the struggle that you're having right now, okay? You're only having an emotional feeling that am I in the right place or not, okay? I told you, okay, you have to trust me, okay? You can either look at the videos, ask your friends, okay? But so far, yes, it's very abstract and where everything is linguistically, you see? Try to be as logical as possible. Try not to add any extra information from what just is written on the board. So build it step by step. This is, you know, if you have this leap of faith, you'll be very happy. As long as you're struggling, okay, it's up to you. Okay, so you do the chance. Can anyone answer that question? Is this circle the same as that circle? No. Now you're confusing the symbols. What is this circle? The name of the map. What is this circle? Nothing. A circ B as a notation is what? Is an element of G, full stop. So all of this is the name. Okay, C. Where C is? What does that still mean? It's actually not defined. The proper way of doing it, okay, if you really want to get rid of this notation, you should actually do it like this. I could say that this is the element C, where C is defined as circ that eats A and B. It's equivalent to the fact that we remember when we had F that goes from A to B, and then I have a map, an element X, and I go to F of X. Is this the same?
Standard way.
Circ here is the name of the map, F.
Between that circle and this circle.
Here, I'm going to make this circ a little bit shaded like this. What do you see? What is the difference between the circ? Nothing. In this way of writing it, it's nothing.
So they both are same.
You take F, A cross B to C.
Sorry?
Probably would make it more clear if you take, for example, F, A cross B, going to C.
No. In this way, a map is always from one set to the other, and this is the element in A, and this is the element in B. That's it. So written like this, okay? Actually, this should be written like that to be 100% precise. You see here, what is A comma B with brackets? It's an element in A. So A comma B in brackets is actually the X here. The F is actually the filled circ, and the brackets are the same as this brackets. That's it. Notation-wise, okay, everything on the top is equivalent to everything on the bottom. Okay? The only fact that an element here is actually comes from 2 is because the domain is actually a Cartesian product of 2 sets. Okay? Clear? Okay. It's simple. I know it's clear, but it's still painful to digest. Okay. So we have to move on. Okay. I'm gonna go back to the old notation. So I'm gonna leave this as the open circ, this as A circ B. So all of this is just the name of the element in G that came from A and B after I mapped them by this map, which is called the circ. Okay. So if I take A after B, okay. So where am I now? What is this an element of? In G. What can I do if I'm an element in G? I can always do what? I can always go again by the map, but with an element C. You get the same result as first starting from B and C and then applying the map circ, and then taking the result and using it with the A like this. Okay? Have you seen something like this before? C, yeah, very good point. Okay, it's a very good question because there's something missing here. What is missing here? What's missing here in this definition, and now you're starting to rewire your brains. There is actually missing what is A, what is B, and what is C. Okay, what I just wrote right now is this is how you read it. Okay, if I act by the map, okay, A by the map circ on A and B. Okay, so I go to this new element, and then afterwards I take the result, which is this new element, and then I act again, okay, by the circ on C. It's equivalent to taking the operation first between B and C, and then taking between A and the result that you get. Okay? So I'll give you a very quick example. 1 plus 1 plus 3 is equal to 1 plus 1 first is equal to 2. The result plus 3 is equal to 5. It's equivalent to 1 plus 3 first, which is equal to 4, plus 1, which is 5. So I get the same result. This is exactly what this said. But in general, without talking about what the set is. Okay. And what is written here, this symbol, you can read it as for all. So this identity holds for all A, B, and C that belong to G. Okay. Another way to look at it is that if I go to the set G and I take any 3 elements, any of them, and I do this left-hand side and this right-hand side, I get always the same result. So it's always valid for all elements A, B, and C in G. Is that clear notation? Okay. So that's the first condition. That's not enough. You need 2 more conditions. There exists, this is what the symbol we talked about last time. So there exists an element, we're going to be calling it E. So an element E in G such that G circ E is equal to E circ G is equal to G for all G in G. So E is an element of G. G is an element of capital G, of the set G. And if I take the binary operation between G and E, G first and E second, or E first and G second, I always get G. I always get the same element. And this is called, E is usually called the, any guess? The identity what? Map? Identity element. Third condition is that there exists an element, we're going to be calling the element G inverse. Now pay attention. What is the inverse here? No, what is the inverse? What is this -1? Just a symbol. You write it with the G to say that there exists some G inverse that lives in, sorry, okay, it's an element in G. It has nothing to do with what you said. Why? What does this imply? What you were talking about? You were talking about a map. G is not a map. G is an element in G, and G inverse is another element in G. Okay? There exists this element such that when I circ G and G inverse, or I circ G inverse and G, I get the identity what? Element for all G in G. Clear definitions? If there is anything that's not clear in the definition, let me know. If you don't know how this relates to drones flying, okay, in the woods, keep that, for later. Absolutely. Perfect. That's exactly how it is.
Of that capital G
Yeah.
should have its inverse element present in the same capital G.
Yes. Yes, right. And what you just said right now is precisely what we also call this element. Usually we call this the inverse of G. What does inverse of G mean? It refers to the element that satisfies this condition for the given G you're talking about. So I start from some G, And there exists always some element in G that I call a G inverse that satisfies this equation. Okay, yes. It is the element, very good question. What the question is, what is the identity element? Is the element that satisfies this.
It's not a one, for example. I mean,
What do you mean by one? So for example, if I have a matrix, what does one mean? If I have a set of matrices, what does one mean? One means an identity matrix? I don't know. So the number one, what does it have to do with the set of matrices? Nothing. You're talking about different sets. You're talking about one which lives in a, is it a natural number? Does it live in the natural numbers? Is it the element of the natural numbers? Is it the element of the integer numbers? Is it the element of the real numbers? Is it the element of the complex numbers? Which one? What are you talking about? Okay. So the pair here, and this is very important, the pair of these two together is actually what's called a group. Okay. Usually we don't say that G itself is a group. You find that in textbooks and in papers, of course. Okay. But it's implicitly defined which group operation you're talking about. And this is usually called the group operation. Okay. So the group operation is the map that satisfies this. If you're lucky to find the map that satisfies 1, 2, and 3, okay, conditions, and then you take this operation with the set and you say both of them together are called a group. There's actually here a fourth condition that's actually implicit. Okay. And it's actually the first one. Let's say that I give you some map I have in mind, and I take one element in G and another element in G, and I find myself not in G. Does this satisfy as a group operation? It's like the zeroth condition. So if I take two elements in G and I do some operation, I find myself I went to set H. Then I cannot call this. It doesn't even make sense to continue with the proof. This is like the zeroth condition. Okay.
I'm not sure that is it necessary to have a group? Like we can only have the group if the image exists. It has any relation with the word image. But we don't.
Do you see it here? Relations are for later.
This sign, second.
Do you see here anything that says image?
Second sign, like with the arrow which had.
This one. This is just the standard notation of what a map is. So this is the set. This is another set. This is an element. This is another element. This is the only difference in notation. Nothing to do with images. Okay. Yes.
multiple values.
Multiple identity elements. I'm not sure. I think the identity element has to be unique. Uniqueness is something we're not discussing here. Okay. And this is something called, you see here, what there exists means that at least one is there. It does not say that there exists only one. That's something else. So what I think this is what you're referring to. No. The condition says there exists an element that satisfies this. Could there be more? Maybe. That's no problem. Is there, some weird proof that actually, for a given set that you always have this uniqueness? It's out of the scope of what we're discussing.
You can assume that you have two. Then if you look at the condition itself, you will see that E1 is equal to E2 actually.
That's exactly, that answers a different question. And now this is, you have to think of what you're doing here. All of what you see here is just a definition. If you satisfy that, you have what's known as a group. What you're talking about is, what are the properties of that? Is there a unique E? Is there a unique G inverse? These are extra conditions, okay? This is usually, so if you have a book chapter, then this will be like the first thing you say, okay, what is a group? And afterwards you would have properties of that. This is, you satisfy this, you satisfy that, and so on and so forth. Okay? So these are different properties of that space. There is a fourth condition. There's something called an abelian group, okay? Which is simply a fourth condition that if you satisfy this, you have a group, okay? Full stop. But there is a special type of group that's usually called an abelian group if you satisfy this fourth condition. And it's simply that A after B is equal to B after A for all A and B in G. If you satisfy this fourth one, then G with the operation is an abelian group, okay? This is just a name, okay? So very quickly, we're going to have a lot of examples, okay? We're going to have the examples now, and then you're going to have time to, you need to go back to home and you need to think about it, okay, a little bit. So, okay. So examples. I'll give you the set called Rn. You know what that is? N tuples. And I'll give you an operation called the plus. This plus operation between n tuples will simply take the first element, okay, in the n tuple and sum it to the second one. And this sum is usually okay, with the normal sum you're used to, okay, between real numbers. Okay? So first one with the first one, second one with the second one, and so on and so forth. Okay. So for example, okay, so A, B, C, E, F, G is defined as, okay, so this plus is actually this plus, is defined as A, B, C, E, F, G. And there are red pluses here. The red plus is different from the white plus. The red plus is a plus between what? Which set? R, real numbers. 1 plus 1, 2.1 plus 0.5, and so on and so forth. But this plus is different, because this is a set that goes from what? So this operation that eats what? 2n tuples. Okay, so it's a different set. Of course, you say, okay, this is an overkill. If I write this one in the same plus, I know what it means. But you know what it means because you're already doing all of this, all of this pre-processing in your mind. But if you're writing code, these are not the same operations. This is an operation that takes some class, and this is an operation that takes another class. Okay, this is again one of the way of thinking about it. Okay, so if I have this operation that you're familiar with, is this an abelian? Is this a group in the first place? Check the conditions. First of all, if I have the zeroth condition is called the closure condition. So if I have one element here and one element there, do I get another element that's an Rn? So the closure is okay, it's possible. I don't get an operation that's an Rn plus 5 or Rn plus 6. I get an operation Rn. So that's the first thing. Is there, if I have first, okay, so let's call of this maybe X and let's call of this Y. Okay. If I add X and Y and then Z, if I add X and Y first and then I add to them Z, and is it equivalent to adding Y and Z and then X? Yes. So that's the associativity condition. Okay, this is the first one that we wrote. What about the identity? Is there some element in Rn that whatever I add to, I always get the same element? What is it? 0, 0, 0. So the E here is actually 0, 0, 0. What you call the zero vector. It's an element in Rn. Okay. Again, we're not using the word vector, but this is what we refer here by E. What about the inverse? Is there an inverse for every element such that when I add this one to the inverse, I always get zeros, which is the identity? What is it? The negative of the same. So, for example, if X is A, B, and C, then X inverse would be minus A, minus B, and minus C. And this minus is actually the inverse of this plus that you're familiar with, subtraction.
Okay, if they were natural numbers, then this would get volume.
Sorry?
If this was natural numbers, it would get volume.
Very good question. Yes. So that's why we're talking about here Rn, the set. If you change a little bit, things get, hard. What? Is Rn the set of only positive real numbers? No. Has positive and negative. Yes.
I find this map as instead of A plus E, could I make it A times E? Using A plus
Do whatever you want. Do whatever you want. That's why I'm asking the question, is this and this, are these two paired together, nothing else with them in the whole world, are these two a group? So far, so good. So we had the associativity, we had the closure, we had the existence of the identity element, and we had the existence of the inverse. So actually, it is a group. So the answer is yes. The fourth condition, is it an abelian group? So if I have A, B, and C, and then I add to them E, F, G, is it the same as adding E, F, G to A, B, C? If I reverse the order, I got exactly the same. So yes, it is a abelian group. Does that make sense? Okay. Another example that's based on that one, okay, and it's trivial extension, is n by n matrices, the set of n by n matrices. And the plus, okay, so that's 2 is 1. So n by n matrices with the matrix addition, what you call a matrix addition, defined as the A11 you add it to the B11, and this is A1 Aij plus the Bij, and so on and so forth. The normal one that you're used to. Matrix addition. Is it an abelian group? It's exactly the same. Everything that we said here follows. What would be the identity element in this group? The matrix of zeros. Is this the same as that? This one lives where? In Rn. Where does this one live? Rn times n. And so on and so forth. Okay. Another example. The inverse would be the minus of that same matrix. Okay. What about Rn times n with what I'm going to be introducing as the matrix multiplication? You all know what that is. Row and column, row and column, row and column. Add this stuff together. You know what it is. Okay. If you don't know, you need to refresh. So matrix multiplication. So that's an operation that takes matrix A and a matrix B. Okay. And now you know how it works. Okay. First question, is it closed? If I have an n by n and an n by n matrix and I do matrix multiplication, do I get an n by n matrix? First condition satisfied. If I have A after B after C, is it the equivalent to A first after B and C? Okay. Yes. So associativity is satisfied. What about, is there exists an identity element? E, that you multiplied by any matrix, you get the same, multiply by any element, you get the same element? What does it look like? 1 here, 1 here, 1 here, and zeros everywhere else. What about the inverse? If I have a matrix A, an element A, does there exist for every element A in this n by n square matrices another element that when I multiply it by A, I get the identity? What? So in general, so what Ibrahim did now is that he found one element that does not satisfy this. So in general, it's not valid for all. Of course it does not, because this is the set of all square matrices. There is another subset, okay? There's a subset of this big set that we call them the set of all invertible matrices. Okay, so what we could do actually, what we can do is that we can define a subset. We're going to be calling it GLNR, and this is defined as all of the sets M. We're going to be calling these sets M, which are elements M in Rn times n that satisfy. We're going to be introducing some map called the determinant of M. You all know what that looks like or how to calculate it. If not, you can refresh. And the determinant of it is not 0. And this is a subset of Rn times n. And if I combine this set with the matrix multiplication, this is a group because we still have all of the identity. The identity actually lives in here. Okay, we have the associativity, we have the closure, and so on and so forth. And there's also another property that's important, that when you have the matrix multiplication of two invertible matrices, the result is also invertible matrix. So actually, I go from GLNR to GLNR. Okay, so I have this closure, and for every element in this set, I am guaranteed to always have the inverse of it. Okay, why does that guarantee it? Because of just this condition. What happened when we added this condition? What did we leave out of our n times n? Exactly. What we just did now is that we said this is the big set of our n times n. Okay, and we're gonna look at a subset of it, which is the subset of all invertible matrices. We took all of this set, okay, and we give it a name. The name is simply, what is the symbol of this set? How do we denote this set? We denote it as GLNR. This is just the name of it. Doesn't mean anything for you now, okay? But usually this is the standard notation for it, because it's usually called the general linear n-dimensional group over R, over the R, and real numbers. Okay, let's put it this way. Okay, you're gonna have more exercises at home, inshallah, in the homework, so that you can play around and test, okay, these definitions. Okay, try to go all of this. Okay, try to think of weird, okay, ideas, weird, thoughts, and ChatGPT is excellent in this. Okay, so, or of course you feel free. Okay, so ChatGPT is your first contact. I'm my second contact. Okay, so thank you very much. See you inshallah next time.